from the details.
Right. So after all these great presentation, we thought it would be nice to kind of win the party with some mathematics. So no, we're both math students, and I guess we were kind of interested in the theorems that you can prove around CAs. So we've seen a couple in the class, like the Garden of Eden, for instance. But for us now, it will be like we'll slightly divert from like actual CAs and allow them to be probabilistic in some sense. So we had, I think, 2 presentations earlier on that talked about stochastic CAs, so probabilistic, and so yeah, we'll go around that and see what kind of theorems we can establish around those. Hopefully, it will do some justice to this paper in 20 minutes and not also smash you with equations. So there will be some pictures, no videos, but yeah. So the starting point is that so these probabilistic CAs, well, the concept is really the same as the CAs that we've seen, except that you allow at the iteration step, the update step, you allow some sort of randomization. So if you look at, for instance, a one-dimensional Taylor automata, you have your update map at each step, and before calling this your new configuration, well, you add a bit of noise, so there's a lot of freedom in how you actually implement that. Or with some probability, you might change the results and end up with your configuration of times q+1. So that's that's relevant in different contexts. Maybe sometimes you want to take the noise actually not too small because I don't know, you have some things that reproduce with a certain probability, or some viruses that spread, or I don't know what. And in other cases, you also might want the noise to actually be very small. So, for instance, I think this is relevant in models of massively parallel computers, where you have some computational error, and you want to study whether actually this is sort of stable. So whether the computations that you perform, well, you're still able to extract some information. And that's kind of what we will follow. So, the concrete example is this: you have this like one-dimensional CA with nearest neighbor updates. So these are pretty much the 256 CAs that we've talked about in the class. And with a small probability epsilon, you just switch the tables. So yeah. So. And then a property that you're interested into is what we call ergodicity, which basically means whether your probabilistic CA retains information in the long run, whether if you had started with 2 different initial configurations. So again, with the parallel with computers, well, if you have some computational errors, well, you still want to keep track of the computations you've been doing. And if everything eventually converges to the same thing, it means that you're not going to be able to remember much about these computations. So an ergodic probabilistic CA is, in layman's terms, defined in that way. So it means that the PCA forgets its initial configuration. Or stated differently, it means that you start with 2 different configurations of x0, and then eventually, after a bunch of steps, it kind of looks the same. So just to put a bit of math, you can see it in both ways. So either as an invariant measure, so something that's preserved by your update map of the CA, such that you start with any initial configuration mu, and eventually it converges to this invariant measure. Or alternatively, you start with 2 initial configurations, and the probability that they are different after a while it becomes 0. So then you can ask the question for, well, already deterministic CA. Oh yeah, so sorry, I forgot to say, ergodicity in the context of with the metaphor of these, with the parallel of these computers is not a desirable property because then you lose the information. And you can ask the question for deterministic CAs already, whether they are ergodic or not. And it turns out that yes, this is a very nice criterion, which is that it's not very hard to see that being ergodic is the same as being nilpotent. So then you're very happy, and then you think about it for a bit longer, and then you realize that this actually is an undecidable property, which is not so bad. I just wanted you have a meme. But,
can you define nilpotent?
Oh yeah, sorry. It means that your update map, if you iterate it a bunch of times, it becomes constant.
Okay.
And by translation invariance, then it's like either 0 or 1. It's easy to see that this is undecidable because of the stopping problems. And the fact that being ergodic is equivalent to being nilpotent is actually not too hard to see that. So because it's deterministic, if you start with two different initial configurations, for them to become the same at some point, well, there has to be some n such that they actually become the same. And actually, the state space is compact, so this n cannot be. It has to be some sort of uniformly bounded over all starting configurations. I guess that's one way to see it. So yeah, let me show you maybe a bunch of pictures. Yeah, and actually something which is interesting, it's just that most one-dimensional CAs, so this is not a theorem, but they are unstable under noise. And by that I mean that it's hard to construct one-dimensional CAs for which the perturbation is not ergodic. There's also a notion of being stable, meaning that I start with a CA, I add just a very small noise epsilon, and I make epsilon go to 0, and I see whether what I obtain, is stable in that sense. But this is also undecidable. Okay. Yes. So some pictures. So you have to imagine in these pictures that the time goes up. So this is the initial configuration. This is the deterministic CA, and this is the perturbed CA, so like probabilistic, but there's very small probability of flipping the values. This one is nilpotent, so you can see that after a bunch of steps, it becomes just all zeros. There are three states actually in that one, like I think white, gray, and black. And in the perturbed one, well, with some probability, you can still be gray or black, but you eventually die out. And both are ergodic, clearly. You start with two initial configurations, and eventually you're not able to tell which one you started from. So this one is also nilpotent, but maybe slightly more interesting because you have these sort of pseudo-fractals. So yeah, this one is also ergodic. This one is a bit different, so it has some like gliders moving at speed +1 and -1, and when they touch each other, they cancel out. This is the perturbed version where you have more gliders. And you can prove that both are ergodic. And actually, these proofs of ergodicity, they always kind of work by just having, so you have different classes of CAs, so like nilpotent. These ones will be the surjective CAs, meaning that any configuration that you want, you can obtain it from a previous one. So that's related to these Garden of Eden theorems. This one, we will talk more about these kind of CAs later on. This is another surjective CA, so the same thing, but you have some like walls that prevents the gliders from they just bounce off, I guess. And then you have a bunch more pictures, but maybe, this one is also, so you have these sort of like Sarah-Pinsky triangles, which is not ergodic because it's not nilpotent, but it's sort of almost ergodic because if you start with a like sufficiently random configuration, well, this, you should like kind of, I guess, converge to some like uniform low eventually. And then the right-hand side, well, when you add some noise gate, everything seems to converge to some uniform thing. Yeah, just maybe. So you will talk about one case for which you can prove ergodicity using entropy theory. But there's also a sort of more maybe hands-on approach that you can take, which is that you want to show that starting with two initial configurations, eventually they'll become the same. So one thing that you can do is that you can actually build what's called an enveloping CA. So a CA with another state, which is like a question mark. And this you have to think about while you initialize the CA with only question marks, meaning that you cannot tell which is the state that you observe. So if you have, like, for instance, two initial data that you start together, they're probably not the same. And then eventually the CA runs, and whenever these question marks disappear, it means that you know that your true configuration will agree on that point, so it'll either be a 0 or a 1. And then, well, you will have established ergodicity if you can show that the density of these question marks goes to 0. So I don't want to specify what's the production rule for the CA, but what you have to, yeah, this is like an example. So imagine this is the configuration you have at some step. Well, what's the transition mechanism for the 0? Well, you know, it becomes a 1. So it doesn't know kind of what the cell is here. But if both, if it were a 1, and if that would mean that 1, 0, 1 would go to 1 with probability 1, and 1, 0, 0 would go to 1 also with the deterministic CA, then you would set the enveloping CA to, well, for this to become a 1 with some probability, very high probability, right? Because whether this would be 0 or 1 would lead to 1. And if not, you would just set it to be some sort of low probability. So this is like the worst case scenario. If just, yeah. So that's how you specify this enveloping CA, and then you just have to study whether this, this density of question marks, it goes to 0, and using first order estimates, just, like what's the rightmost point with the question mark or something like that. You can already prove ergodicity for some basic CAs, like having a two-size neighborhood. You can prove for almost all of them that they will be ergodic with small nodes. Yeah, that was it for my part. So
This would be.
Oh yeah, sorry. So just for the ergodicity of the noises here, so there are different types that when you combine these two, they become ergodic. We just chose, I chose to talk about the surjective and additive noise because that was the case that I found most interesting, at least for me. It uses quite nice techniques. It uses the entropy technique. So as Philémon explained, the surjective CA, in a few words, it just means that the global map that I will have here is going to be altered. And then I will define what's an additive noise. It's if I can take like all these states and then map them to some random group, and so it's just going to be some sort of addition of a value in that group, and so you add these values independently at each site. So this is what I mean by additive noise. So there is this theorem that I'm going to try to give a bit of a sketch of a proof. It's proved in 2017 that every perturbation of a surjective CA with a positive additive noise is ergodic with the uniform Bernoulli measure as its invariant measure. So the principle of ergodicity is that you converge to some uniform measure, and here it's just going to be Bernoulli. I'm not going to really explain why is it Bernoulli. I'm just going to give why it's ergodic and it converges to a measure, basically. So the proof idea is just that ergodicity is due to the accumulation of information. So basically you just forget everything else that happened before, and then you can't really take any sort of information. And then, a good measure to know how much information we know, it's the entropy, Shannon entropy. And so I think, is everybody familiar with the concept of entropy, or should I introduce it? Okay, less work for me. So here, again, with the same graph, so I have this cellular automata, I have these sites that I will explain later, just to get these windows to afterwards know exactly how the entropy on these sites behave. So the Bernoulli measure is stationary. What I mean here by that is that it's stationary after I apply n, and also with the noise. It's as the structure of the additive noise, it's preserved. I don't know how to really say it, but after even you apply the noise, the uniform Bernoulli measure, it's still a uniform Bernoulli measure. And so here, to prove the ergodicity, so on each site, I just have to prove that this entropy on this information is just going to converge to basically what I will say the maximum of the elements here, capacity of each site, product with the site, which makes us with ergodicity.
Can you maybe explain how do you compute this h of xtj?
So Okay, so this xtj is just like that you apply t, the transformation, and then the j is just for the site that the window that I am doing the computations on. And so basically the principle of ergodicity is that afterwards, like on each site, I'm going to converge to the same thing. No, just like when knowing the length of the site somehow.
But so this h is computed as kind of if you run the system many times up to t,
Yes.
you look at the thing and then you compute the distribution of this and you compute the entropy of that.
Yes.
Okay.
Exactly. And so the h is just going to be like the maximum capacity. Anyway, so and then we will have just to use some bootstrap lemma just to say that if this entropy will, I mean, in some sense, I'm going to say that it's not going to, when you're working with the surjective CA, it's not going to erase the entropy, but rather diffuse it. And so the techniques of the proof would be to have some sort of a sharp estimate of the entropy on finite sets. And so the technique here used, it's very similar to finite Markov chains. I think it's a very well-known lemma that uses the entropy. So this is some sort of just like a direct application of what happens if you use the same thing. It's just like that, it grows exponentially. And so we just have to prove that this thing is small enough so it goes to 0, and so I just get rid of this thing. And what I mean by that j is just some sort of a boundary that I have on each side. So this is, I want this to be small enough so I have this thing that goes to just GH inverse state. So that's basically, I think, no. So here I just try to explain a bit what I mean by like the effect of both things, because as I said, it's surjective CA with additive noise. So how does that work on the entropy? So for the surjective CA, as I said, it just diffuses it. So it's just going to depend here. So YT is just after I apply the function t and xt plus 1, then I add the noise. So it's just going to have this sort of inequality that also depends on the window I chose. And then the effect of the additive noise, this is the result that really comes from the finite Markov chain method. I think it's also a method that was used beforehand by Boltzmann, like it's very similar to something used in physics. It's not like a very new technique or groundbreaking, apparently. And so yeah, that's we have, as I said, it just grows exponentially faster. So the kappa here will just go to 0, and then we just have that this thing will be relatively small. And using some fancy technique, we'll prove that this is equivalent to being ergodic using this bootstrap lemma. And then that's about it, actually. This is how you prove that it's ergodic. So yeah, thanks. Hope it was not too much questions.
Any questions?
I'm sorry, I'm not sure I understood why the surjective CA diffuses entropy and not. I know you explained it, but
Okay, yeah, sure.
Diffuses entropy and not.
Erase it.
Or maybe not increase. I don't know. Maybe I don't know. I really think it increases it because it's surjective. So each time it isn't maybe the information that was before. I don't know. But I'm not super at ease with this concept. So,
No, okay. It's actually a very good question. I think why this doesn't work. Well, for the entropy, it's like, okay.
Well, so the thing, probably first of all, being subjective means that you're essentially injective in that case, right?
Yeah, like about the Gardner theorem,
So you're
yes.
bijective.
Yeah.
Yes. So then if you're injective, you just have the extra noise coming from the next step, right?
Yeah.
Right. So it's a property rather of the bijectivity because of the Gardner theorem.
Yeah.
And remember, there is some caveat, right? You have some local injectivity instead. Right, Barbara, or
If you're surjective, it implies you're pre-injective, but not necessarily injective.
Yeah, there is this.
Injectivity implies surjectivity, but surjectivity implies pre-injectivity, which is where you prove injectivity.
But I think in this case, I read that it's bijective by the Garden-Eden theorem. I mean,
I think if you're a finite system, it's
Yeah.
the same, right? Or,
I think it's like because it's compact as well.
What's pre-injectivity?
Pre-injectivity means that if you have that it's injective, then you just constrain yourself to a subset of initial configurations, and that would be those that only differ only from finite.
Yeah. So if you restrict to a compact state, pre-injective is equal to injective, right?
Okay, so
So this is on compact
Yeah,
world.
it's on
or-
compact.
Yeah,
Otherwise,
no,
you
then-
can choose like dynamical, like an ergodicity theorems on here because you need. That's like what gives the whole ergodicity thing.
Then okay, then it's bijective, and so you kind of preserve the total
Yeah.
information, right? And so you can kind of diffuse it.
it's budgeted, so I didn't hear the word it's budgeted
Because of the Garden of Eden theorem.
Yes.
So you can show that surjectivity implies some weaker form of injectivity.
But if you
but-
restrict it to some sort of finite thing, which is the case here, because otherwise we can't talk about and really see it as a dynamical system, then it will give the bijectivity. Okay.
I have a question which is a bit more general. So it's just about ergodicity to understand, both of you, whoever wants to answer. So the question is, so ergodicity in some way, if I kind of relate it to the classes of Wolfram, both a periodic CA and a chaotic one would be ergodic, or am I wrong in that?
So deterministic, you say?
Yeah, deterministic.
Well, none of them, I think.
None of them?
No, I
Okay.
don't
Because
think so.
to be ergodic, it has to be nilpotent in some sense. Because
But that's what I didn't understand, because here in this, yeah.
it's periodic, and I start with like two initial data with like two different states of the period, and they'll never meet, right?
So this is because the kind of the distribution that you have at each step flips each
Yes.
frame.
Yes.
So
Yes.
that's why it's not ergodic.
Yes.
Okay, I see. But for a chaotic CA, okay, you mean it's deterministic, so you don't have a distribution, it's always kind of a Dirac
Yeah.
delta, the distribution that you get, and that's why you cannot converge to kind of Bernoulli or something like that. Okay,
I
I
don't
see.
think so.
In a way, yeah, okay. Because I could say, like, for example, for a chaotic one, if I kind of average over 20 time steps, then over these 20 time steps, I get some sort of kind of constant distribution. But okay, it's not the same definition of ergodicity.
No, I don't think so. Also, like the definition, I think here it's done is really like with regards to the measure and how like I don't know.
Because the measure is just kind of the probability distribution on the next pixels, right? If I understand correctly or not.
The measure of
The measure that must be invariant by the evolution of the system.
the measure is on your initial data.
Yeah.
And the,
Okay, exactly. Yeah. So if it's deterministic, it's kind of okay.
But if you
no
have a
probability.
deterministic CA with a deterministic initial condition,
Yeah.
Yeah, you
Okay.
can't really.
Okay, I see. Okay. Yeah, so that was the question. So when you say ergodic, you say that you get the same measure. So it just means you get the same measure at some point in time, not from different initial conditions. If it's at some point in time, you get the same measure.
yes.
Not at the same time steps.
What do you mean?
When do you get this invariant measure doesn't matter. You just need it to happen sometime.
It's in the limits.
It's in the
Okay, in the
limit,
limit.
like when you do that.
Because it's for like an arbitrary window also, right? You like
Okay.
sample your initial data is on Z, but then you want it to like on whichever window you sample it, well eventually it has to look the same.
Okay.
So if
Okay.
there was this example with like the like pyramid, right? Like
Yeah.
this thing for
Right.
like finite window, eventually you see all white, but like,
Right.
if you're able to like scale the window as you iterate the thing, of course, you still see.
So the reason it's ergodic on the right-hand side is that the distribution is just the random noise for each pixel.
Exactly.
Yes.
Okay. Yeah. Okay. Any other questions? Right. So yeah. So the last thing, I think you already answered this, but just to make sure. So this ergodicity property, in this case, it was only for finite or kind of compact grids.
Yes.
Right?
Yeah.
Can you also define it for infinite grids? I mean, it makes sense.
I don't think so, because I think you will need the compactness. I don't know.
Just for defining it.
What would it mean then to be? Because I don't think anything would be ergodic in that.
Yeah.
Well, for example, if you have a CA that no matter what, each cell will be dead after 5 time steps.
Okay. So then for deterministic CAs, I would guess that this like ergodicity notion would be some also like being like uniformly nilpotent or something.
Yeah.
I don't know what
Okay.
I see.
Okay. Yeah. I see what you
surely,
mean. Yeah.
I mean, so you can adapt actually.
It's just ergodicity in general is defined for finite systems, or
Yes. Ergodicity in general, like for dynamical systems, you have to have the compact. At least compact, because otherwise you can do like all these fancy theorems that will give you the convergence. There's also another problem of how does it converge, if it does converge uniformly or not.
okay.
And that's a question I think you can only have the tools to answer it if it's a very
Compact.
nice and compact thing.
Okay.
That's it.
Last questions? If not, okay. Thank you.